Welcome to Oil and Gas with Energy Law Prof. Today we're going to talk about a case that's about natural gas storage. But before we do that, we need to talk a little bit about why natural gas storage has become so important, not just in Texas, but in the United States as a whole, and increasingly in the world. And one thing that we're going to see is that over time, natural gas transport and storage is just going to grow more central to the global economy. And I want to talk about why that is. So historically, as we've discussed, the global economy has really run on two commodities. One is coal for electricity and industry, and the other is oil for transport that makes globalization possible. If you look in the United States, we've actually moved to a lot of natural gas for electricity, but those three fossil fuels, oil, coal, natural gas, have really driven the U.S. economy. Now, if we want to talk about the policy goals that we have going forward, one of them is to clean up our energy system. And so to move from those traditional sources like oil and coal to cleaner sources like natural gas and like electricity, especially from renewable energy. And when you think about how much cleaner those are, you could think about just what it's like to use them in your home. You should not be burning coal or oil in your home, but many of you will use natural gas and electricity very safely in your home. Of course, you want to be safe with those, but they are simply much less polluting sources. So if we could transport our energy system to be based on them, it would potentially be much cleaner. And we're trying to do that. So one thing that we're trying to do is have more cars that run on electricity rather than on oil. And we're trying to take our electricity sources and make them run more on natural gas and renewables rather than on dirtier sources like coal. So we have this transition toward more reliance on electricity and more reliance on natural gas and renewables for those clean sources. Now, what I want you to understand is why that is putting such a premium on natural gas transport and storage. And the first reason is to understand that, unfortunately, if we take that spectrum from dirty coal and then oil to cleaner natural gas and renewable energy, unfortunately, it's the same spectrum from easy to transport oil and coal and difficult to transport natural gas and electricity. So one of the reasons that oil and coal were able to build the modern world is that they are very easy and cheap to transport and store. And that might seem like, oh, just a convenience, but in fact, that is crucial to the reliability, the affordability, and the security of the global energy system. And you can think about it this way. If you have a shortage of oil or coal, it is very easy for other folks around the world to send you the oil and coal that you need. And as the price rises, where you're having that shortage, they will naturally send that oil and coal to you. And that provides a lot of security, reliability, and really smooth prices to the oil and coal system. By contrast, if you have a shortage of natural gas and electricity, there is no way to get you the natural gas and electricity you need. So if you want to send natural gas, you have to send it by a pipeline. It's going to have to be an airtight pipeline. That's probably going to cost billions of dollars. If you need to send natural gas overseas, you're going to have to liquefy it, which means cooling it down most of the way to absolute zero till it becomes a liquid 400 times smaller, can be put on a vessel. That vessel has to be refrigerated, can be sent overseas. That facility is likely to be costing about $30 billion, and that vessel is likely to cost $250 million. So it's a very expensive process. There is no fast way to send you more natural gas. Now, the same thing is true with respect to electricity. There's only one way to transport it. You have to send it by a power line that's going to be difficult to build, can't be done on a short time period. So if you have a shortage of oil or coal, there's lots of ways to send it to you, tanker, truck, rail. Not the same with electricity and natural gas. And we're going to see some of the challenges that creates. The other thing to say is it's not just about transport, it's also about storage. Because oil and coal are very easy to store, they're relatively energy dense, you don't have to worry about them escaping to the atmosphere in the same way you do with natural gas. We can prepare for shortages in the future. So it's very easy to store oil so that we can use it if there are future shortages of oil. In fact, just in 2021, just last year, we relied heavily on our stores of oil. In fact, for that whole year, on average every day, we were consuming 100 million barrels of oil. But on average every day, we were only producing 98 million barrels of oil. So we were 2 million barrels of oil short every day. 2% short. How did we even manage that? Well, we had higher prices, so there were some downsides, but basically we lived off of our stores of oil. And that's the flexibility that commodity that's easy to store provides you. We don't have that flexibility with natural gas and renewable energy, but we'll talk about how we are trying to provide it. So there is a move to rely more on electricity for other needs in our economy, energy needs in our economy, because it can be a cleaner source if it's provided from cleaner sources of electricity. So we're trying to move transport, i.e., electric vehicles. We're trying to create electric vehicles rather than ones that run on oil products like gasoline and diesel. We are trying, in some cases, there are places that are trying to move heating from sources like oil and natural gas to rely on electricity as well. Well, where does that electricity come from? Well, increasingly, it comes from two sources. The biggest, by far, in the United States is natural gas. And if you were to divide electricity production in the United States into fifths, 2/5 would come just from natural gas. Then you would get 1/5 each from renewable energy, from nuclear, and from coal. But if you look at the trends in sources, what you see is that increasingly we're relying on natural gas and renewables. And what I need you all to understand is that means basically relying solely on natural gas as a reliable source of power. And we'll talk about why that is. So if we look at what kind of sources of power are being built over the most recent years, well, what we can see here is above the line, if you go from 2005 to 2020, and this is where it turns from data into a projection. In that history, you see that mostly what was built is these natural gas plants in light blue. It says oil and natural gas, but vast majority are just natural gas. And then in green, wind power plants, and in yellow, solar power plants. If you look at the projections going forward, again, it's basically just natural gas power plants, wind plants, and solar power plants. Now, what you can see is below the line, what kind of sources are we retiring? And what you see is a lot of, in black, coal power plants. So we're relying less on coal as time goes on. And if you look at the projections going forward, you see increased projections to retire nuclear power plants, and so to use nuclear power plants less. Well, one thing I need you to understand is that these kind of power plants that we're retiring are very different from the new kinds of power generation sources that we're building. So both nuclear and coal power plants, to a first approximation, basically they're on or off. They just go on and keep running, providing power. Renewable energy is very different. We don't get to choose when we get solar power. We don't get to choose when we get wind power. And often, neither are really available. So we can't count on them to provide power. And we'll see some of the challenges that creates. Natural gas is a little bit different from those sort of just on or off sources, because it's more like the power in your car, where you can kind of run it with more power or less power. It can ramp up or down. And that makes it actually a pretty good match for solar and wind in theory, because basically when solar and wind aren't available, it in theory can ramp up to take its place, and it often does that. Now, you need to think carefully about how difficult it is to balance electricity demand and supply over the course of the day. So I'm going to give you an example of a single day in California. It happens to be March 26, 2017. And this is showing you midnight to midnight. And what you can see from the overall height of this graph is how much power is demanded over the course of the day. And maybe, as you would expect, starting from midnight, people are going to bed. You get a minimum of power use, at 3 a.m., 4 a.m., 5 a.m. in the morning. But as people wake up, the electricity use increases, and then when people come home at the end of the day is typically when you have the biggest use for power. Everybody gets home, turns up the AC, plugs in their phone, etc., maybe plugs in their Tesla, and so that's when we have the most power demand. Now, I want you to look at the biggest source of renewable energy here, which in yellow and light green is solar power. And what you can see is during the middle of the day, solar power is providing a huge amount of the power on California's grid. And that means that we can run those other power plants less during the middle of the day. So that's helpful because it means we save natural gas. But if you look at the early evening hours, when power demand peaks, solar provides no power during that period of time. And so all of the power demand has to be met when solar isn't available by those other sources of power, and principally going forward, that's natural gas. So natural gas has to be the source that we can depend on to provide power, but those other sources, we often think about them as fuel-saving sources. They're sources that allow us to use less fuel at our natural gas power plants, but we can't really shut down the natural gas power plants if we want to make sure that power is available when it's needed. And in fact, we don't really have a choice about that. The power grid has to exactly balance how much power is being put on the system by all the power plants with how much is being demanded every time you flip on a switch, every time you plug in your phone, every time the air conditioning kicks on, every time that you turn on your dishwasher. That has to be exactly matched by power supply from the power plants connected to the grid. If they are even slightly out of balance, what happens is that the frequency of the grid changes. So the frequency of the grid in the United States is 60 hertz. That means it's alternating current 60 times per second. If that gets even a little bit out of whack, as we'll see it did in Texas during the Texas storm of 2021 and the blackouts, the whole grid will go down because basically none of the machines that are connected to the grid, none of the power plants that are connected to grid can operate if it's even slightly out of balance. And that makes electricity really a kind of fragile system because of that need for instantaneous balance between power supplied and demanded at all times. Okay, that is particularly challenging because, as you could see with that picture in California, often these solar and wind sources that we're building more of don't provide power when we absolutely need it most. So I think, as many people know, if you look at this top GIF, you can see a wave of solar power going across the United States that peaks at noon, and of course it's completely absent when the sun isn't up. But I think maybe fewer know that wind also has a daily pattern, diurnal pattern, that extends over the United States, where there is much stronger wind energy in the early morning hours. And you can see that sweeping across the United States in those hours before dawn. Unfortunately, that's when we least need power. And so one thing that many may not be aware of is solar power is often more valuable than wind power, even if wind power can be produced more cheaply, because solar power is more likely to be produced during the middle of the day when we need a lot of power. Now, one challenge is neither of these sources is particularly likely to be strong in those early evening hours when we often most need power. And so that's why we obviously have to have other sources that meet that demand. Now, we can see some of the challenges that created during the Texas blackout. So this is a picture of the Texas grid for the first 2 weeks of February before the blackouts hit the early morning hours of February 15th. Now, first, what I want you to see is on this first week of February, the Texas grid operated as it was supposed to. In red, you can see that wind power was providing a lot of power to the grid. In general, wind power provides about 25%, about a quarter of Texas's power sources. But then you can see that the grid, also as it's supposed to, when that wind power wasn't available, natural gas in orange filled in those gaps. And so that's how the Texas grid is supposed to operate. Now, what happened in the second week of February? Things got cold. And that created a number of challenges related to some of the long-term trends that we've just been talking about. So one big challenge is often when it gets very cold or very hot, wind doesn't produce very much power at all. And so you can see for that whole cold period, wind fell down to very low levels. And in fact, wind power, which normally provides us with about 25% of our power, at times was providing as little as 2% of the power on the Texas grid. So we know we can't rely on those sources, and so natural gas is supposed to be a reliable source that provides the power that wind can't during those periods. And you can see that during that first week of cold, natural gas did what it's supposed to. It ramped up and up, providing more and more power to the Texas grid. Now I want to talk about the second trend we talked about. We said we're relying more on renewables for electricity, but remember, globally, there's also a push to rely more on electricity in general, and for very important human needs like transport, things that you might need in an emergency, right? To heating that you might need to avoid freezing. Well, Texas is actually far ahead on that trend in the sense that it relies more on electricity for heating than most U.S. states. We rely a lot on electricity for heating. Unfortunately, electric heating isn't very efficient unless you have newer heat pump sources that are really only starting to be distributed. So in general, most electric heat not very efficient. And so that means that to heat people's houses when it gets cold, you need a tremendous amount of electricity. And you can see with that record amount of demand that was created on the Texas grid at that time, that there was just a huge strain on the grid to provide this power. It was requiring unprecedented amounts of power, but at the same time, the wind power sources that we normally rely on weren't available. And in the early morning hours of February 15th, night of Valentine's Day, the Texas grid basically broke. And why did it break? Well, remember how I said you have to exactly balance how much power is being provided with how much power is being demanded. Well, that grew out of balance because of this unprecedented demand for electricity, for heating, and because at some point we couldn't get enough natural gas to the plants that needed it to keep providing more and more electricity. So because of the difficulty of providing natural gas and the fragility of the electricity system that requires exact balance, we had a problem. And so we had less power going on the grid than we had power being demanded from the grid. What happens? As I told you, the frequency of the grid starts to fall. It fell from 60 hertz down to 59.3 hertz, only about 1% lower, but that was enough to start causing some power plants to trip off of the grid. As soon as they go off of the grid, that means, of course, there's even less power being provided, and it starts a chain reaction. To stop that chain reaction, the regulator in Texas, ERCOT, cut people off of power, and from then on we had 4 days of blackouts. But I want you to think about the contrast with these new energy sources and our reliance on them versus those traditional energy sources. So for an entire year, we were 2% short of oil. That had some bad consequences. Oil prices went up, gasoline prices went up, diesel went up, etc. But there were no terrible shortages. We basically got through it just fine. Now, think about, by contrast, being 2% short for an entire year. The Texas grid was short of electricity it couldn't balance its frequency for 4.5 minutes. Just 4.5 minutes where the frequency was only 1% down, and it caused this week-long disaster. And so that just gives you a sense of, because we don't have instantaneous balance. We don't have just stores of electricity to draw on, because we don't have just stores of natural gas to draw on. The system ends up being a lot more fragile, and that's particularly a problem when we're relying on those newer, cleaner energy sources for things that are really crucial to human survival, to our economy, etc., like heating, like transport, etc. So to the extent that we rely more on those things, this will get even more challenging. So, because it is difficult to transport natural gas from place to place, that means that we tend to get big differentials in the price of natural gas in different places. Often we'll talk about what's the price of oil today, or what's the price of coal today, and we'll talk about just one global price. That's because oil and coal prices may vary a little bit around the world, but it's basically pretty similar, because if the price of oil gets much higher somewhere, it is relatively easy to ship them more oil, and over time that will tend to equalize the prices. By contrast, with electricity and with natural gas, it is you can't really equalize those prices. You get big price spikes where you get very different prices in one place than the other because there is no short-term way to get more electricity to Texas if it has a shortage. You can't just build a new power line in an emergency. That's not a possibility. And so one characteristic of these natural gas and electricity markets is we see a lot more volatility in prices. Prices vary a lot more in geography as well. So this is just a picture. Just happens to be 2014, but it's a picture of natural gas prices in different places around the United States. And you can see that a lot of those places have relatively similar prices. So they're connected by pipelines. If prices rise one place versus the other, they just ship more. But there are times when there's not enough capacity on the pipeline to bring one of these places all the natural gas they need. And there's no short-term solution to get them that natural gas. So natural gas gets bid up to very high prices during those periods. And you can see that on that chart here with those two trading locations, New York and Massachusetts, getting to prices that are 5 or 6 times what you see for the prices. Usually in the US, when people talk about just one price, they're talking about Henry Hub, but it's important to understand those prices vary from place to place. Now here's the same picture for the world, and you can see very different prices around the world, and you can see at times when there's plenty of natural gas transport to serve everyone that's needed, then you may have somewhat similar prices. But often, there are very different prices around the world, prices 2 or 3 times higher because there are shortages in one place and we can't get more natural gas to those places until we can build more of those $30 billion liquefaction facilities and those send liquefied natural gas vessels overseas to address that shortage. So that is a huge challenge. Even if we can do that, because of the expense of doing that, prices don't completely equalize. So we see much different pricing geographically. And you can see how dramatic it is because when we talked about those 2 hubs that are in New England, in fact, I mean, they are very close to one of the biggest sources of natural gas in the world, which is the Marcellus Shale. And so often we have this kind of anomaly where the most expensive natural gas in the world is in New England, and the cheapest natural gas in the world is just a couple hundred miles away down the road in western Pennsylvania. Obviously, that would never happen in oil markets. The reason it happens in natural gas markets, the same thing kind of thing can happen in electricity, is because sometimes we don't have enough transmission of both gas and electricity to meet those needs. So, historically, although natural gas prices can spike a lot, historically there has been sort of a cap on them that is because of oil. So oil is very versatile. We typically think about in the United States using it for transport to create gasoline, diesel, jet fuel, fuel oil for ships. But you can also burn it for electricity. And in fact, old natural gas plants typically have the ability to run on oil as well. And that has meant that if natural gas prices spike too much, as they kind of tend to do, then you would just switch to oil instead. And if we look at this graph, which is showing 2010 to 2018, what you can see here is this is showing prices of different energy commodities, but in terms of how much energy they carry, in terms of MMBTU. And what I want you to see is for most of this period, the high price commodity is Brent. That is oil. It's oil valued in the North Sea between the UK and Norway. But you can see that basically is a ceiling on prices for the other commodities. The other commodities that are listed here in light blue, we have coal. You see that's a relatively low value commodity. And then all the other lines, the orange line, the blue line, the black line, the green line, are all different prices for natural gas. As we know, those vary a lot in different places. The orange line is that Henry Hub price, which is in Louisiana, so close to the U.S. Gulf Coast. That blue line is the UK price. That black and green line are the prices in Asia. And so you can see those Asian prices tend to be highest, but none of them tend to break above that Brent oil, at least not for very long. Well, the reason for that is that if they get that high, just switch to using oil instead, because oil gets you more energy per dollar. When oil gets you more energy per dollar, you can always burn oil. So historically, that has been a cap to those natural gas prices. And that actually is what New England relies on. So New England burns a lot of oil for electricity in those periods where they get spiking natural gas prices. Now, the world, because of our general trend away from those dirtier sources, is actually losing that capability to rely on oil as sort of a backstop ceiling for the price on natural gas and thus electricity. And there's a couple reasons for that. So one reason for that is that newer natural gas power plants are typically optimized for efficiency, for environmental performance, to only run on natural gas, not to run on oil. And so they don't necessarily have the ability to just switch to oil like those older power plants did. Secondly, we are increasingly imposing environmental penalties on burning oil instead of natural gas because that emits more carbon, more air pollution, etc. And so that has created a situation that has never happened before but will likely happen a lot in the future, which is that now in many parts of the world, we're seeing natural gas prices spiking well above the oil prices. So here, that Brent price we looked at before, or that West Texas Intermediate price, are here you can see, because oil is relatively easy to transport and store. They tend to be a little bit smoother, not as spiky, and they tend to go together. But what you can see here is the JKM price, which is an Asian price for natural gas, and the NBP price, which is a United Kingdom price for natural gas, are much higher and for an extended period than oil. And this is really the first time that's happened, but it may happen a lot more in the future as we move to stop relying on oil and just rely on natural gas as well as a cleaner source of energy. So if we're going to do this successfully, the only way we're going to be able to do it successfully is by building a lot more transport and storage of both electricity and natural gas. We're talking about natural gas today. So one way that we're trying to build more transport of natural gas is through this huge boom of liquefied natural gas facilities in the United States. So the United States, in just the last 5 years, has gone from not exporting liquefied natural gas at all to the number one liquefied natural gas exporter in the world at the start of this year, 2022. And you can see that incredible ramp up in natural gas production. Most of that liquefied natural gas capacity is on the U.S. Gulf Coast. But one thing that makes it particularly helpful for creating some liquidity in the global energy system and for providing flexibility and price smoothing is that it has the ability to sort of ramp down, and you can see that in 2020 during the pandemic, and then ramp up again when natural gas is needed. So that is starting to make the natural gas system a little bit more like the oil system, where because we have plenty of transport, we get smoother prices, fewer price spikes, fewer regional differentials. Now, it's never going to be as smooth as oil because it's simply more expensive to transport natural gas. But the more liquefied natural gas transport capacity we build and the more storage we build, the more likely that we're going to be able to have a more reliable, secure, and smoother priced energy system. So, we talked about transport. Let's talk about storage of natural gas. How do you store natural gas? Well, if you haven't liquefied it, right? If you liquefy it, then you have to refrigerate it. It's very expensive. So typically, natural gas has to be stored underground because it is so voluminous, right? Before you've liquefied it, it's so voluminous that economically speaking, typically you have to store it underground. What are your options for storing it underground? Well, here on the left, you see you could use a depleted oil and gas field. It previously held natural gas, so it should be tight for natural gas. You plug whatever wells are in that reservoir, you pump down natural gas, and you can store it there. In the middle, you see salt formations. Some salt formations themselves can hold oil and gas, but you can, that is typically impermeable to gas as well. You can store natural gas there. Now, in places that don't have salt formations or depleted fields, another option is a depleted aquifer. Just because something holds water doesn't mean necessarily it can hold natural gas. So, that's not always going to work, but that's an option that we see in places like the Midwest where they don't have depleted oil and gas fields. And you can see that storage around the country in this map. You see those depleted fields all around the oil country, Texas, Oklahoma, California, Colorado. Those are those brown triangles. Those green triangles are salt domes. You see a lot of those around the Gulf Coast. And then in the Midwest, you see a lot of natural gas stored in those aquifers, those blue circles. So here's the case that I wanted to talk about natural gas storage. This is Texas American versus Citizens Bank. There is part of this case is really about financial law, but the real issue that we're looking at from an oil and gas perspective is who owns natural gas that is injected into an underground storage reservoir. And what's happening here is the Kentucky court is dealing with sort of a silly precedent that had suggested that when you produce natural gas, if you were to store it in a field, well, you basically returned it to nature. And so if your neighbor wants to drill a well and produce all the natural gas, pulling the natural gas away that you stored, well, that's just rule of capture. They get to keep it. And so the court says, no. You can't. If you produce natural gas, it's sort of like the animal that you've tamed and that principle of animus revertendi that we talked about. That means that nobody can take it from you. It's no longer in that state of nature where it can be captured. Now, there's still an important issue that occurs when you have injection of natural gas on one party's land, but they're using a reservoir that underlies multiple parties. And so there's this question of how we compensate those other landowners whose pore space is being used for storage of that natural gas. That's a question that's also arising in the context of storage of other products, including carbon dioxide, et cetera, which is stored to prevent that carbon dioxide leaking to the atmosphere and contributing to climate change. So there is a question raised in your book about, well,